Okay, to begin our third segment here with chapter 3. Chapter 3 is kind of a shift in directions. And we are going to cover now composition of substances and solutions. And this is kind of a mishmash of different things like the formula weight or formula mass and the concept of moles, which is a quantity that's very important in chemistry, and also things like concentration and that kind of thing. And solutions, of course, are also known as homogeneous mixtures. The first portion of the chapter deals with formula mass and the mole concept. This is sort of a preparation for working with quantitative information in chemistry. And quantitative information has to do with how much stuff you have or how much of each substance is present if it's a mixture. Qualitative, on the other hand, is the kind of stuff that we're doing in this week's lab experiment, which is more like, what is it or what is it like? Quantitative is when you put a specific value on the quantity, how much do you have? Whereas qualitative is more like, what do you have or what is it like? The formula mass for a compound is something that we've actually kind of gone over before, but it would not hurt to review it. The formula mass would be based on the molecular formula or the formula unit for an ionic compound. And it's just the sum total of all of the atomic masses of all of the atoms in the formula. So for covalent substances, substances in other words that exist as separate molecules, the formula mass is also known as molecular mass or molecular weight. Technically, it's really mass, but we often use weight interchangeably in chemistry since, unlike the physicists, we're not going to other planets or anything like that. So gravity doesn't change, and we can use weight and mass interchangeably. So for example, the compound glucose has a molecular formula of C6H12O6, and the molecular weight or mass would just be taking up the masses of these elements from the periodic table and multiplying each by the subscript in the formula and adding them all up. So if you have C6H12O6, you can look at each of the elements separately. For carbon, you've got 6 of them in the formula. And the atomic mass of carbon from the periodic table would be 12 atomic mass units per atom. And 6 times 12 is 72 atomic mass units for the carbon in each molecule. For hydrogen, you've got 12 of them in each molecule. And each hydrogen, according to the periodic table, has a mass of 1 atomic mass unit. And so that would be 12 atomic mass units for the hydrogens in the molecule. And for the oxygens, you've got, again, 6 of them. And there are 16 atomic mass units for each average atom of oxygen. And so that would be 96 atomic mass units for the oxygen. And when you take 72 plus 12 plus 96, you get 180. 180 atomic mass units per molecule would be the molecular weight or molar or molecular mass rather of the compound glucose. Atomic masses in the periodic table are given in different periodic tables with different numbers of decimal spaces. In most cases, for our purposes, it would be okay if you want to round the atomic mass in the periodic table off to the nearest whole number. But there are cases where we might need to be more accurate, in which case we might need to use more decimal places. Most periodic tables, like the one we use, I believe, usually gives 2 decimal places, but some give more. And there are tables where you can look these numbers up that will have even more than that. And so you can be very accurate if you really need to, be. For ionic compounds, remember ionic compounds exist as 3-dimensional networks of alternating positive and negative ions. And the overall ratios the lowest whole number ratios of positive to negative ions are what we write down as the formula for the ionic compound. And they don't exist as separate molecules. So what we have to do is come up with our so-called molecular weight, or say formula mass, will be just the mass of the atoms present in each formula unit of the compound. And the formula is basically the empirical formula, or the lowest whole number ratio of the element, or of the cation to the anion. So the formula mass is just the mass of the empirical formula, or the mass of one formula unit of the compound. If you have calcium chloride, which has the formula CaCO2, then for calcium, you've got one of them, and the periodic table says that an average atom of calcium has a mass of 40.1 atomic mass units. That would mean 40.1 atomic mass units for calcium. And you've got two chlorides. And so you've got two chlorides, and each of them has a mass of 35.5 AMUs, which is 71 AMUs for the both of them. And when you add those up, you get 111.1 atomic mass units per formula unit for this compound. Again, since ionic compounds technically don't exist as separate molecules, it's technically not correct to refer to this as the molecular weight or molecular mass. But for most purposes, we kind of use the terms interchangeably. If you have sodium sulfate, then you've got two sodiums at 23 atomic mass units each, and one sulfur at 32.1 atomic mass units, and four oxygens at 16 atomic mass units. And when you add all of that up, you get 142 atomic mass units per formula unit. And what I really wanted to show was something like calcium phosphate, Ca3 parentheses PO4 close parentheses 2. In compounds like this, you have to be careful when you're adding up the number of atoms of each element. Calcium, obviously, you've got three of those, okay? And the periodic table says that each calcium has an average atomic mass of 40.1 atomic mass units. So that's 3 times 40.1, or 120.3 atomic mass units for calcium. For phosphorus, you might be tempted to say there's only one phosphorus in this compound, but actually there are two, because remember, there's one phosphorus for each phosphate ion, but there are two phosphate ions. So for phosphorus, it's actually 2 times 1, or 2, and each of them has a mass of 31 atomic mass units, so that's 62 atomic mass units for the phosphorus. And then for the oxygen, it's not 4, it's 2 times 4, because each phosphorus ion has 4 oxygens, but there are 2 phosphorus ions. So that's 2 times 4, or 8 times 16 atomic mass units for each oxygen, which is 128 for the oxygens. And when you add all of those together, you get 310.3 atomic mass units per formula unit for this compound. It's also important when you're dealing with compounds that have waters of hydration, it's important to include the waters of hydration in the formula mass for the compound. So in CuSO4.5H2O, those H2Os are present and they are clinging to the matrix in which CuSO4 is found. And basically what you've got is a 3-dimensional matrix of alternating copper ions and sulfate ions. And for each, basically on average throughout that matrix, for each combination of a copper ion and sulfate ion, you have 5 water molecules clinging around them. And so those 5 H2Os are there, and as long as they're there, you have to count them. So for copper, you've got 1 of them, and that's 63.6 atomic mass units each. For sulfur, you've got 1 of them, and that's 32.1 atomic mass units. For oxygen, You've got 4 for the sulfate ion, but remember, you've also got 1 for each H2O, and there are 5 of those. So for oxygen, it's actually 4 plus 5, or 9, times the mass of each one, which is 16 atomic mass units. And then for water, or hydrogen rather, you've got 5 times 2, 5 H2Os with 2 hydrogens each. That's 10 times 1 atomic mass unit each. And then when you add these numbers up, you get 249.7 atomic mass units per formula unit for copper sulfate pentahydrate. So just be sure you include those H2Os in the mass. When you're finding the mass of ions, there's no need to account for the gain or loss of electrons in ionic compounds because the electrons are still present in there. If you have something like sodium chloride, you know, of course, the Na ion is losing an electron, but the chloride ion is gaining that same electron. So that electron is still accounted for in the formula, and you don't have to worry about it. Also, even if the electron did go someplace else and was completely missing from the formula, each electron is only about 1/1800th of an atomic mass unit. So even if you completely skip the mass of the electrons, it would still be pretty accurate. You know, the mass that you do come up with would be pretty accurate. Okay, so that's usually pretty simple. Moles is a concept that a lot of people have trouble with, even though it's actually not that difficult. It is fairly simple, but a lot of people seem to think that it's not. So we'll see if we can, I'll see if I can convince you that it actually is a simple concept. Now, remember, first of all, we are not talking about burrowing rodents here. That would be biology. Here, we're talking about a quantity. The word mole is derived from the word molecular Gewicht, which is my best attempt at pronouncing the German word, which means molecular weight. And the mole concept is really just a quantity that makes it easy to convert between the mass of a substance and how many atoms or molecules are in that sample. And that's something that can be quite useful in chemistry. The mole is a very important concept, so important that the American Chemical Society, the professional organization for chemists in the US, actually uses a little stuffed mole, a stuffed toy mole, not a real stuffed mole, as its mascot. And it's sort of a silly looking little thing with a lab coat and goggles on and a beaker in its hand or paw. And it's really thoroughly silly. And if a stodgy sort of uptight organization of professional scientists like the American Chemical Society is willing to embarrass itself like that by using a mole as its mascot, then you can tell that it must be a pretty important concept. Mm-hmm. In fact, let me see if I can show you. There he is right there. Kind of silly, huh? Well, if the ACS will, again, embarrass itself over the mole like that, then it must be a pretty important concept. And it's definitely one that we're going to want to be familiar with. Okay, so a little moment of humor over with. Let's get into the mole. One mole, like I said, it's a quantity. And it often helps when you're first learning it if you think of it as analogous to a dozen. A mole is just a number of items, and it doesn't really even matter what those items are. A mole is always that same number of items. Just like a dozen is always 12 of something, a mole is always 6.022 times 10 to the 23rd power of items, whatever those items are. And that's known as Avogadro's number, after Amedeo Avogadro, whose work with gases led to the calculation of that number. And that particular value for the number was chosen because it happens to be the conversion factor between atomic mass units and grams. So in other words, if you have 6.022 times 10 to the 23rd atomic mass units, you have 1 gram. And since, say, a proton or a neutron is 1 atomic mass unit, that would mean that, for instance, 1 proton or 1 neutron equals 1 atomic mass unit, and 6.022 times 10 to the 23rd protons or neutrons would be equivalent to 1 gram of protons or neutrons. And the really important and useful thing here, try to fix my crippled star there, also means that in the periodic table, the masses can be read as atomic mass units per atom or as grams per mole of atoms. Okay, so if we look at the periodic table and we see that copper has an atomic mass of 63.55, that means that each copper atom on average has a mass of 63.55 atomic mass units. But it also means that if you have 63.55 grams of copper, then you have 1 mole of copper, which is 6.022 times 10 to the 23rd atoms. So that can actually be quite convenient to be able to tell how many atoms you have, or molecules if it's a compound, just based on what the mass is and looking at the masses in the periodic table. Okay. Before we get into calculations involving that, we'll just look at the fact, I want to remind you the fact that really a mole is just a number of items. It's a quantity, like a dozen. 1 dozen is always 12 items. It doesn't matter what the items are. It could be a dozen eggs or a dozen bowling balls or a dozen atoms or a dozen planets. It doesn't matter. It's always 12. 2 dozen would always be 2 times 12 or 24. 2.5 dozen would be 2.5 times 12 or 30 items, and so on. Well, the same with a mole. 1 mole, and it doesn't matter whether it's a mole of atoms or a mole of eggs or a mole of bowling balls or a mole of planets. Okay, we're getting into, I don't know if there are even that many planets in the entire universe, but anyway, theoretically, I guess you could have a mole of planets. Well, 1 mole of something, anything, is 6.022 times 10 to the 23rd of whatever those items are. 2 moles would be 2 times 6.022 times 10 to the 23rd, or 1.2044 times 10 to the 24th items. 2.5 moles would be 2.5 times 6.022 times 10 to the 23rd. That's 1.5055 times 10 to the 24th items. So we're dealing with numbers here that are not as convenient as 12, but it's the same concept. You could, you can even look at it going the other way, from the number of items to the number of the collective quantity that we're using. If you have 26 items, how many dozens do you have? Well, you'd do that, you'd divide by 12, right? 26 items times your conversion factor, which would be 1 dozen for every 12 items. This way, the unit of items cancels out, and you end up finding out that you've got 2.17 dozens of items. Well, if you have 7.85 times 10 to the 25th items, how many moles do you have? Well, you just take that number divided by Avogadro's number, 7.85 times 10 to the 25th items, times your conversion factor, which is 1 mole for every 6.022 times 10 to the 23rd items. Trick here, remember, if you're dividing on your calculator, if you're dividing by a number that itself contains a mathematical operation like times, be sure that on the calculator you use parentheses around the number you're dividing by. So 7.85 times 10 to the 25th divided by parenthesis 6.022 times 10 to the 23rd, close parenthesis, hit equals, and you've got 130.4 moles. And as I was saying a moment ago, you can look at the periodic table and notice that 1 atom of copper has a mass of 63.55 atomic mass units on average. That just means 1 mole of copper atoms would have a mass of 63.55. And if you have some other mass then you can divide it by that number to find out how many moles you've got. Then you can multiply the number of moles by Avogadro's number and find out how many atoms you've got. And we'll see examples of that in a moment. Works the same way for compounds, except you'd have to use the formula mass or the molecular mass for the compounds instead of the mass straight from the periodic table. For instance, one molecule of water has a mass on average of 18 atomic mass units. That's taking 16 for the water and 2 times 1 for the hydrogen. That gives you a total of 18 atomic mass units. Well, it's also true that 1 mole of water, or 6.022 times 10 to the 23rd molecules of water, has a mass of 18 grams. This is really convenient because 18 atomic mass units and 1 molecule are quantities that are way too small for us to be able to deal with conveniently. But a mole, or 18 grams of water, that's something that's really easy to measure out, and you can see it and you can appreciate it. You can measure it accurately and you can use it in reactions, and it's just a very convenient quantity. And so if we have that much, we actually know how many molecules we've got, which is also very useful to know. And so we can now basically relate the macroscopic quantity of mass of a substance to the microscopic quantity of number of atoms or molecules. And we do that by way of moles. Anytime you want to go from mass to number of items, whether they be atoms or molecules, you have to go by way of moles. If you want to go from number of items to mass, again, you have to go by way of moles. Either way. Okay, so you could say, if I have 0.5 grams of copper, how many copper atoms do I have? Well, again, if you're going from a mass to a quantity of individual items, then you have to go by way of moles. So the first thing we would do, how many moles would correspond to 0.5 grams? And so we take 0.5 grams of copper times the fact that there's 1 mole for every 63.55 grams of copper. Grams of copper will cancel out, and we end up with moles of copper as our answer, 0.007868 moles of copper. But we didn't want moles of copper, we wanted copper atoms. And so we can then take that number of moles times Avogadro's number, and we find the number of copper atoms. So it's 0.007868 moles of copper times the fact that there are 6.022 times 10 to the 23rd atoms of copper for every 1 mole of copper. And we get 4.738 times 10 to the 21st copper atoms. That's how many we have in 0.5 grams of copper. Interesting thing to know. On the other hand, if you have a specific number of molecules and you want to know the mass, you again have to go by way of moles. So what if I have 3.16 times 10 to the 22 molecules of glucose? Because you can, you've got a really good magnifying glass and you can count really fast. How much does it weigh? Well, we can do that too. But again, you have to go by way of moles. So in this case, we take the number of molecules and divide by Avogadro's number, just like if we wanted to find the number of dozens, we would divide by 12. Okay, so we got 3.16 times 10 to the 22 molecules times 1 mole for every 6.022 times 10 to the 23rd molecules. Notice how molecules cancels out, and you end up with moles of glucose as the answer for this step. And if you want the mass, then you just take the moles of glucose and multiply by the molecular mass in grams per mole, which would be 180 grams per mole, just like when we figured out the formula mass for glucose, it turned out to be 180 AMUs per molecule. That's the same as 180 grams per mole. Okay, so the number of moles times the number of grams per mole. Notice how moles of glucose cancel out, and you end up with a mass, 9.445 grams of glucose. Okay, so that's how you can do that kind of thing. There are many more examples in the book. And I will have the homework assignments for chapter 3 very soon. Having said that, we're about up to time on this segment of the video now. So I think I will leave it there, and we'll start with section 3.2 next time. Okay, until then, that'll be Thursday. And until then, I'll see you later.